Each picture is another revelation, and each will provide mankind with a perspective on the universe that we've never seen. Today addresses an intriguing new part in the investigation of our universe. This telescope is one of humankind's perfect designing accomplishments. The deeper you look, the less you comprehend ought to be the adage of our cosmology, particularly in the presence of James Webb. The beginning of a new era in space science has begun as the world gets its most memorable glance at the full capabilities of the James Webb Space Telescope. In a mission more than 2 decades in the making, NASA sent off the most costly science experiment ever assembled. A $10 billion telescope that will endeavor to capture starlight from the first galaxies to be brought into the world in the red-hot cauldron of the Big Bang. Despite encountering many delays, the Webb telescope has finally delivered the goods. However, the latest pictures captured by the Webb telescope are sending shock waves through established scientists as they call our entire understanding of system development into question. All of a sudden, we realize that we might need to revamp all the textbooks about the start of the universe. Join us as we dive into Webb's newest pictures alluding to one more universe at the edge of the universe. The generally accepted understanding of the universe is this: around 13.8 billion years ago, the Big Bang occurred. In its initial seconds, the rules of physics as we understand them didn't apply. All that would eventually become matter burst forward in a matter of seconds. First particles like electrons, photons, and ultimately neutrons and protons, the building blocks of our molecules. Early seeds of stars, planets, and universes expanded out from that groundbreaking moment, and space itself spread so that the universe turned out to be deeply smooth. Perfection on an immense scale simply means that things inside the universe are relatively uniformly distributed. That is, if you were to put a cube around one part of the universe, it wouldn't be much more dense than another randomly put cube. On a smaller scale, like between galaxies or within a planetary system, matter is knotty and filled with clumps. Physicists measured that not long after the Big Bang, something called inflation happened. Basically, what was once a little packed-together universe expanded out rapidly in a mere fraction of a second, and it keeps on expanding today. Inflation is part of the ongoing standard model of the universe, called the lambda cold dark matter (LCDM) model. In LCDM, the shape of the universe's expansion looks towards some depictions like a funnel. It's wide at the top, growing and spreading farther out over time. That's one interpretation, but there are others that have emerged from the very clues that scientists can actually observe and measure. Observational astronomy, in fact, that data is crucial if scientists are to use models to make real predictions about the future of our universe. Theoretical astronomy is about ballpark estimates that are shaped by the few things we actually do know for sure. Something called the cosmic microwave background adds to a big piece of that observable data. The cosmic microwave background is made up of the echoes of radiation left over from an early stage of the universe. Radio telescopes can pick it up and then translate the waves into an intensity map, a picture of sorts. This image actually shows us how the objects in the universe were distributed around 400,000 years after the Big Bang. The earliest observable glimpse of a universe without stars, planetary systems, and galaxies. Everything was closer together and almost uniform, except for small fluctuations that became the matter-forming stars and galaxies. This picture serves as evidence that the universe started packed together and has expanded to where it is today. We also know that the universe continues to expand, and we might measure to some degree how fast it's doing so. The cosmic microwave background also serves to confirm that an earlier version of the universe was very hot and our time is a much colder one. One method of testing this model is by checking very distant galaxies out, identical to looking back to the first few 100 million years after the Big Bang that started it all. The universe was simpler then, its development simpler to think about against expectations. Cosmologists first tried to see the earliest patterns of the universe using the Hubble telescope. In 1995, over 10 days, Hubble captured 342 openings of an empty-looking patch of space in the huge scoop. Cosmologists were shocked by the overflow hiding in the inky darkness. Hubble could see thousands of galaxies at various distances and evolutionary stages, ranging back to much earlier times than anyone expected. Hubble would go on to discover some very distant galaxies. In 2016, astronomers considered its most distant one, called GN-Z11, a faint smudge that they dated to 400 million years after the Big Bang. That was surprisingly early for a galaxy, but it didn't fit in with the LCDM model, partly because the galaxy is tiny with only 1% of the Milky Way's mass, and partly because it stood alone. However, when the James Webb Space Telescope came along, our narrative of the universe has been thrown into turmoil. NASA's $10 billion bet in full operation since summer 2022 has shown the galaxies formed much earlier after the Big Bang than researchers previously suspected, and that some of them are surprisingly huge. Discoveries have thrown the entire academic community into a new reality in which their current theories no longer apply. The earliest and most massive galaxies seen by James Webb so far stand to go against the prevailing thinking in cosmology. Researchers estimate that each galaxy is seen from between 350 to 1,000 million years after the Big Bang, and each more than 10 billion times as large as our Sun. One of the galaxies even appears to be more massive than the Milky Way itself, despite our own universe having billions of additional years to shape and evolve. That means if most are right, we're in strange territory. We'll need something very new about galaxy development or a change to cosmology. One of the most extreme possibilities is that the universe was expanding faster shortly after the Big Bang than we anticipate, which could require new forces and particles. Because we believe we understand how gas that's ionized-based matter falls onto these early galaxies and how star formation feeds back and keeps future gas from falling in. There's a limit for how fast material can accumulate onto these objects, and although certain conditions can lead to an object temporarily overcoming that limit, it should not be sustainable over such long-term scales. Indeed, we usually see a maximum of 10% of gas converted into stars, but for galaxies to form so quickly at such a scale, they would also need to convert nearly 100% of their available gas into stars. While 100% conversion of gas into stars is technically right on the edge of what is theoretically possible, it's still the case that this would require something to be very different from what we expect. Many people immediately say that standard cosmology may be all wrong and perhaps we should throw out the Big Bang as the explanation for the origin of our universe. They suspect new laws of physics like a new early form of dark energy that existed early on, or new physical oddities like the universe being born with extremely massive black holes, or new exotic forms of matter like a novel stable particle that decays into normal matter at relatively late cosmic times. While many people believe that this explanation is entirely absurd, that isn't the case. Remember that even before the historic launch of James Webb, various problems emerged with our current standard model of cosmology. As follows: the nature of dark matter. One of the fundamental problems with the LCDM model is the nature of dark matter itself. Dark matter has not been directly observed. Its existence is inferred from gravitational effects on visible matter and the cosmic microwave background. Despite extensive searches using various detection methods, including direct detection experiments and indirect galactic observations, the particle or particles that comprise dark matter remain unidentified. Dark energy and cosmological constant. The inclusion of a cosmological constant, lambda, to account for the accelerated expansion of the universe is another contentious point. Initially introduced by Einstein and later discarded, lambda was reinstated after observational evidence suggested an accelerating universe in the late 1990s. The challenge lies in reconciling the tiny value of lambda predicted by quantum field theory with the observed energy density of dark energy, leading to what is known as the cosmological constant problem. Structure formation and simulations. While the LCDM model successfully predicts the large-scale structure of the universe and the distribution of galaxies, discrepancies arise on smaller scales. Simulations of galaxy formation sometimes overpredict the number of small satellite galaxies around larger galaxies like the Milky Way. This missing satellite problem suggests that either our understanding of dark matter is incomplete or the simulations need additional refinement, such as including baryonic physics, standard matter. More accurately, cusp versus core issue. Another issue within the LCDM framework is the cusp versus core issue in the density profiles of dark matter halos. Simulations tend to predict a cuspy central density profile for dark matter halos, whereas observations of dwarf galaxies and other structures indicate a more spread-out core profile. This discrepancy raises questions about the effects of baryonic input processes, such as supernovae and black hole formation, on dark matter distribution, which are not fully understood or included in current simulations. Tension in Hubble constant measurements. Recent measurements of the Hubble constant, which describes the rate of expansion of the universe, have indicated a persistent tension between values obtained from local measurements using objects like Cepheid variables and those inferred from the cosmic microwave background by missions like the Planck satellite. This tension suggests potential shortcomings in our cosmological models, including LCDM or systematic errors in measurements that are yet to be resolved. Beyond these specific challenges, the LCDM model also leaves unanswered several fundamental questions in cosmology. For example, it does not account for the nature